Lukas Seidel. He's going to be presenting today on a really innovative approach, I think, to firmware rehosting and fuzzing. So if you're not familiar with firmware rehosting, I was kind of blown away when I first was introduced to this topic. I didn't think that so much was possible. Marius, another one of our guest speakers, is going to his original research that I saw was kind of mind-blowing, and this is kind of taking that to another level, providing orders of magnitude speed up over some of the traditional approaches. So I think you all are going to find this really enlightening. So please welcome Lukas.
Thank you. Yeah, welcome. My name is Lukas. And today I will be speaking about rethinking emulation for fuzzing or for fun and profit. I will be talking about near-native rehosting for embedded ARM firmware. Quick overview, what we're going to be discussing today. So for those unfamiliar with embedded firmware fuzzing and also rehosting, I will introduce that. Then we're coming to an overview of different approaches to firmware rehosting. We will discuss some of the performance roadblocks, which actually motivated us to do this research. Then I will be introducing the name-giving near-native rehosting. Our engine we built on top of that principle, and then discuss performance and also some drawbacks and outlook, and finally the conclusion. Small motivation for this, there is a full paper if you're more interested on this. I worked on this together with Dominic and Marius, who was also giving a talk at this conference later. And yeah, the whole framework is open source. You can check it out, the evaluation, all the experiments we ran. So yeah, stay tuned. So we have an embedded system. This embedded system has a CPU, and that CPU is running some firmware to get all the systems going, to do whatever or to help achieve whatever that embedded system was designed to do. Usually in these embedded systems, you have some way of interacting with the world around you. You have sensors, you have antennas, stuff like that. And all these peripherals have to interact with your firmware one way or the other. They usually do this via MIO, memory mapped input-output. And now we want to fuzz or analyze this firmware running on this embedded chip, and you usually do not want to fuzz the actual hardware. That's painstaking. You have to reset after each cycle. You have no good way of getting coverage. You have no real introspection. So one thing, how that is usually tackled nowadays is to rehost the system. That means you take the firmware, emulate the CPU around it in a user-space process in your emulator. Think QEMU or Unicorn on top of that. Maybe you've heard that. And then you have a fuzzing engine supplying the firmware or the peripherals, that is, via the peripherals with MIO with fuzzing input. So you want to test out all the different functionalities of the firmware. So I don't know, imagine your firmware is interacting or has a Wi-Fi antenna it is using to connect to the internet, so you could supply fake Ethernet frames via your fuzzing or from your fuzzing input via the model peripheral via MIO. So now we will be discussing some rehosting approaches, how all of this is being done, because usually you do not have a good model for all the MIO peripherals there are, right? Like think QEMU. QEMU is able to model or to emulate many peripherals there are, but of course not every single little last sensor or every last Chinese or whatever embedded system you can get. Like there are so many, you cannot have a model available for all of these. So you have a way to supply your MIO input with more or less good and valid input. So one way how to achieve that is you take the actual hardware and you just run it. and you log all the MIO accesses it's doing, and you're logging the MIO values you're seeing, you're checking if you can what these MIO values are doing, and then you replay those values, or you build a pattern-based model on top of those values, or you even train a small machine learning model to then supply these or similar valid MIO values during fuzzing back to the emulated and rehosted firmware. Second approach under the subcategory would be symbolic constraint-based approach. So think symbolic execution. You handle unknown peripheries by returning symbolic values. Fuzzware, which is the state-of-the-art approach doing this and implementing this, is using some lightweight program analysis to reason about all the places where MIO accesses are being done, where peripherals are being accessed. It is running a lightweight symbolic execution, which is heavily constrained to avoid path explosion. So it basically only executes that code that is in the context of a specific MIO access. And then you have symbolic values for all your possible MIO register values that could occur and could have actual meaning behind them, because just putting in like random fuzz input into your MIO will not yield much coverage inside your firmware. Second option, which we will explore more deeply later, is high-level emulation. So the basic idea is very naive. You're not having a fancy model or anything, but you do a lot of manual work. So you really need to know your firmware. You really need to have it reversed, or in some cases, maybe you have source code available. And then you have to hook every place, or you have to place a hook at every location where there is a function trying to access MIO peripheral. And then you model these accesses in a high-level language. So you're just simulating the behavior that MIO accesses is supposed to achieve, or the effect is supposed to achieve, by hooking that function, implementing the same logic without actual supplying real MIO values. So on this side, on the right side, you see a Rust implementation of a handler function for fopen. So imagine you have rehosted an embedded firmware, but you do not have a real file system underlying that during fuzzing. So every time you try to open a file on your fuzzing, on your file system, what we're doing instead is you construct a fake file object. You see that struct on the down right, and you just take fuzzing input from your fuzzer and put it in there. And then you return that instead of actually reading from file. This is working surprisingly well, of course, if you do it correctly. But as I said, a lot of manual work. This is a nice taxonomy of all the different firmware rehosting systems there are. This is from a different paper, not from ours. You see on the top, there is QEMU over pretty much everything, over pretty much every approach. All of them are using that one emulator. Some of them are using Unicorn, but Unicorn is also just using QEMU under the hood. You see on the bottom right Hallucinator, which is very similar to the approach we used in the end. So this is also HLE, so high-level emulation based, what I just talked about. You see in the middle, you see Fuzzware, which is the aforementioned state-of-the-art using symbolic constraint-based approaches. There are also, on the very left, for example, there's Firmware, which is a specialized emulator specifically for baseband emulation and fuzzing. So there are many systems out there trying to achieve different sub-goals of this huge field, all of them implementing new ideas. It's very interesting. Yeah. As I just said, and as you saw, most of these are based on QEMU, and that will lead us to some performance roadblocks I will discuss now, and why we actually felt it would be interesting to rethink the emulation we're using in rehosting. So QEMU is doing binary lifting in emulation. It is a full system emulator. You have a firmware for some embedded chip that is usually not the same architecture than your host system is running. Yeah, usually you have x86, 64, for example, on your everyday laptop. And yeah, on the embedded chip, you find ARM or something like that. So the guest code is lifted to an intermediate representation, tiny code. Then you add a bunch of instrumentation around that. That is then JIT compiled back to host code the host system can actually understand. So it is a rather long pipeline. And now you might be saying, yes, of course, but nowadays we have like caching and execution chaining, and there are all of these performance optimizations around QEMU. And yes, there are a lot of optimizations, but I would say none of them were initially designed to account for fuzzing, where we really want to execute something at thousands or tens of thousands of executions per second. And also, many of the systems you just saw in the taxonomy are based on AFL QEMU. So that is a fork that doesn't have basic block caching, and it doesn't have execution chaining. So a lot of these nice optimizations are actually not there. And yeah, that just costs you a lot of performance. Other thing is dispatch of memory accesses. So QEMU was intended, as I said, as a full system emulator, at least one half of it. So it is general purpose. It is meant to emulate or being able to emulate everything you throw it at. It has a soft MMU, which it uses to dispatch memory accesses, but there is no real need to emulate an MMU for a system that doesn't even have an MMU in hardware. So this is just costing us performance without even the need for it, in the case of many embedded firmware. Yeah. Last thing is that many of the aforementioned fuzzer approaches are not using in-process fuzzing, so they are heavily forking. And like, imagine for every execution of the program, it just forks instead of respawning or like resetting the state or respawning a new execution of the fuzzable target inside the same process. We are forking, and that means a lot of context switches into kernel, and context switches are also super expensive. With that, we come to near-native rehosting. So the intuition here is a lot of embedded firmware runs on ARM v7 chips. I do not have the exact numbers, but there are studies on that, and it is a lot. And especially if we reduce that to everyday systems you actually use and not to some super obscure, I don't know, system, not many people, but yeah, a vast majority you find out there is ARM v7 chips. Second observation is that there are ARM v8 cores that provide access and compatibility to the same instruction set, so to AArch32 and thumb instructions. ARM v8 cores are usually 64-bit, but they can understand the 32 ARM instruction set. So why not use that? So we're doing exactly that. We are executing the firmware meant for small embedded devices on their bigger brothers, because we can just lift a lot of the instructions without touching them at all. We do not need an intermediate representation. We do not need to recompile or JIT compile them back to the host system, because guest and host system are basically the same. And with this, we can just outperform many of the recent rehosting approaches that just rely on whatever off-the-shelf emulator you can find or that they did find. Yeah, and that allows us to go really, really fast. With that, we come to our actual implementation of this approach. Safirefuzz, originally meant to mean same architecture, firmware rehosting, and fuzzing. And this is an overview of that. So you have, again, a user space process. So all of this is happening in Linux user space. You have one process that has 2 copies at some point of the firmware target we want to fuzz. So on the right-hand side, you can see one copy, which is the actual target that is being placed in memory at the exact same location you also place, or the original firmware would be placed on the embedded firmware. That means you need to do some You need to set some flags and some kernel options to allow you to actually map memory all the way down to address 0, because usually Linux doesn't allow you to do that. Then you copy it there, and then you start executing. And just every time you take a basic block, you copy the basic block in the range of memory where we actually execute in the end, and then you just check if you encounter an instruction that you actually need to rewrite. And there are not many you actually need to rewrite. You here see also that there we have these HAL level abstraction layers. So HAL is hardware abstraction layer functions. Think, I don't know, STM32 embedded systems. They come with SDKs, they come with libraries. All these libraries are there and ready to be used to access the various peripherals. So that is a very good and fast way to find places where the firmware is communicating with external peripherals via this HAL. And exactly that is the place where we want to place our hooks, where we want to place our abstractions and model that and like the behavior in a higher level language. And then we have also libafl, which is doing the fuzzing part. So mutation engine, we have coverage guidance there, stuff like that. So to the design, yeah, one thing I already mentioned a little bit. So we have basic block rewriting. We're doing runtime instrumentation because static instrumentation is incredibly hard, especially in ARM. In x86, there are enough tricks because of the non-static length of instructions to achieve what you want. But in ARM, there's no general way, or there's, in the general case, it's unsolvable to replace every instruction in place. And yeah, because our host system is understanding the instructions of our guest system, we only need to rewrite a small minority of all instructions, namely PC modifying instructions and PC relative memory accesses, reads and writes. Second thing we're implementing, of course, is hooking. We need that for the high level abstractions. We are implementing function hooking, not instruction level hooking, just because it's easier. And also turns out you can implement nearly every functionality, virtually everything, just with function hooking. Function hooking means we always assume that we are the first instruction of a function being called. That allows us just to make some assumptions about the state and about the state we need to save, we have to save and reset. And overall, this allows us to do the whole context switching, which is still happening in the same user space process, right? Like there's no real like kernel user space context switching. But between engine and executed target in just 5 instructions. And then we have interrupt approximation. We have no real interrupt-based system that is very hard to implement. This is following the approach we saw in Hallucinator, the state-of-the-art for high-level emulation. And the observation is that many of the interrupts which are actually important and we actually want to see being executed and handled are often have to do with MIO accesses to external peripherals. So we want to hook those anyways. And then you can approximate many interrupts just with ticks. So you have a manual tick counter, and you say every n ticks, you check if there is an interrupt to be triggered. You can place these tick counter hooks then, for example, in infinite loops. I have many of those in embedded systems, just listening for incoming packets, for example, on Wi-Fi antenna. You could imagine that you just place a tick counter there and then say, okay, every n ticks, please trigger this interrupt. And in many cases, this will give you a lot of coverage in the target without being super realistic. We are aware of that, but it does its job. So now to the basic block rewriting. I mentioned before there are only 2 categories we actually need to rewrite. Here both are shown. So on the left side you have the original basic block. The first thing you see at OX1004 is a PC relative memory access. We are rewriting that to load from an absolute address. So that is also another reason. Remember I mentioned we have 2 copies, like the rewritten basic blocks and always retaining the original target in place, so we can always address data in the original target by its absolute address. Second thing is we are then encountering a branch on equals, so that is a PC modifying instruction on the last instruction on the left block, and that we are replacing with a jump back in our engine because now we do need to do a bunch of stuff here. So one thing is we need to rewrite both successor blocks, so for branch taken or branch not taken, and so now we're here, right? Like we're rewriting successor 1 or successor 0 and successor 1. And then we're also doing a resolve branch where we're emitting a static branch to the rewritten new basic block. So from the rewrite BB, we got the new address of the rewritten basic block, and then we replace these in the branch. So that is here the resolved address. Then you see here the final rewritten basic block after its first execution. So this is before its first execution, after it initially being rewritten and emitted. And here we have after the first execution. After the first execution, we insert this branch to just skip the jump back into the engine, so we can, on following executions, just leave out a lot of the instructions we don't need anymore. And yeah, from this, an interesting question might be, okay, why do we need to actually modify these PC relative reads? Why do we not just copy the data with it? Like, shouldn't be easy? No, it's unfortunately not easy because in ARM, you have a lot of these interleave data chunks. So between basic blocks, or at least like function block boundaries, you'll have a lot of just, data chunks, which are being targeted by these PC relative reads and writes. That is an optimization and space compressing thing that ARM does that is useful, but finding these interleave data chunks is super hard if you do not know the basic block boundaries beforehand. And as we're doing runtime instrumentation, you obviously cannot know that at the time you actually need to do the rewrite. That is why we're opted for just resolving this into a static read or write from a static address. Second thing, very interesting, caused me a lot of headaches. So processor cache maintenance. Some of you might know, many or some I would assume not if you haven't worked with ARM at such a low level. So ARM v7 8 cores, and also I think many of the V8 cores, they have separate caches for instructions and data. And these caches are non-coherent, so they are not guaranteed to hold the same information at the same point of time. So you are allowed to modify the code you're executing at runtime. That's just self-modifying code, right? But no one is telling the instruction cache that you actually did. And that will work for a long time. I don't know, I've seen millions of instructions being executed as I thought they would, until some point they didn't, and I had no idea what was going on. Like I saw divergences in the CFG, like I was at some point just back in the engine where I absolutely didn't expect execution to be back there, but somewhere totally different. And then I saw that the functions or the instructions being executed were not the same I just wrote there like a couple of seconds before. You actually have to tell your CPU to refresh the cache. So after each time rewriting a basic block, you have to invalidate the iCache. Small performance evaluation on this. So overall, we evaluated this on 12 firmware targets. Here you see 6. You see that for a majority of targets, we achieve more coverage or comparable coverage in like a fraction of the time. Like in the first couple of seconds to 2 minutes, we have on many targets more coverage than other fuzzers had or rehosting systems had after 24 hours. That is really good. We also accounted for differences between the fuzzing backends. Like you can see that we evaluated against Hallucinator, but also a new version of Hallucinator where we replaced the AFL++ backend with a libAFL backend, so exactly the same fuzzing backend we used. And you still see that for many targets, we're still way faster, more coverage. You also see target on the bottom left, so for the P2IM drone, where we didn't find any meaningful coverage at all. I think that just means that was a bad harness. Yeah, so it really depends on your rehosting harness. You really have to understand what the target is doing and how you have to emulate the behavior of external peripherals for this approach to work. And if you don't, more automatic approaches, like in this case, symbolic constraint-based fuzzware, they just might be better. Yeah, as I said, overall 12 targets. Each target we tested 5 times on 24-hour runs. We did a bunch to try to verify fidelity. So we rewrote a lifting or rewriting engine from scratch. Like there's a lot of room for error, but all the actual abstraction layers and hooking, we did like 98% identical to what Hallucinator is doing, just for the sake of being able to compare. So like we could execute targets on our engine and then rerun the same input in Hallucinator and just compare that we hit the same checkpoints at the same point in time, in the same order. That helped us a lot, and it looked like, yeah, everything made sense. We are able to reproduce crashes between both rehosting systems. Like you can have a crash in Hallucinator, take the input, throw it into Safirefuzz, and it will crash again. Yeah, just to make sure that, just as a sanity check for this approach. And overall, we were able to be 690 times faster than Hallucinator, which is like state of the art in high-level emulation, and 145 times faster than Fuzzware, which is a different approach, but they're of course also doing rehosting and fuzzing, so we're comparing against them, of course, too. I think that is just really cool. Like, of course, there are many factors here. It's probably not just QEMU versus what we're doing, but I think it is overall, like it shows the premise of this approach is it makes sense. And if you're not convinced by the actual approach, I think at least it makes sense to say, think about what you're fuzzing and think about the specifics of your target and build a fuzzer as tailored as possible for your actual use case, wherever you can. Yeah, some potential drawbacks, I mentioned that before, so the manual effort is immense for new targets. In this case, we only evaluated against targets we had already some kind of ground truth for. And yeah, implementing realistic handlers is hard. Fidelity, you have to be very sure to make no big mistakes. We tried our best efforts to make sure that there are no huge divergences here. Interrupt approximation, it is not super realistic, but it does cover many code paths, and that's actually what you want in fuzzing, right? And the code paths triggered are actually they're realistic. They're not achievable, or not any code paths you cannot achieve in real time. We also checked that. It's usually just a trade-off against automation. Fuzzware has a mode where it has very high automation. You can just throw in the target, don't have to do anything. But with a basic configuration, you might not achieve that much coverage. If you want to do that, you have to tweak the symbolic execution model here and there. It's always a trade-off. Other thing, future work, real quick. I think it would be a lot of fun to replace the high-level emulation-based approach with MIO, with a symbolic execution approach, just taking that from Fuzzware and plugging it into our rewriting engine. And the second thing would be to look at snapshotting, whether that can actually benefit us in execution speed even more, even if embedded targets, like the whole boot up process, usually it's just a couple of thousand instructions, but still might be nice to check this out and see if we can gain more speed here. And with that, yeah, our conclusion, optimize your emulator wherever you can, specific to your target. Near-native execution can go very fast. It can help you rehosting and fuzzing ARM v7 M targets in Linux user space. Interesting fact, there's another team who had the same idea, so it might be not totally bogus or just academia. So I think it's a sweet idea to explore, and it allows you to go really, really fast in fuzzing. GitHub, you can find our source code and experiments there. Thank you for your attention, and open to questions.